Okay, so we need to finish up our notes. We don't have that much more to talk about, but a couple of new things. So, last time we did not get, I kind of skipped ahead and we didn't do problem 4. It's an important problem. So let's do problem 4 right now. Determine whether the series converges. If it converges, give the sum. Now notice that all of these series are infinite. So if we are going to give a sum, we're going to use that formula. That's our geometric infinite series formula. Who remembers, though, the key component to using this formula? What has to be true of R?
It's got to be less than 1.
Has to have an absolute value less than 1. In other words, the terms of the sequence need to be decreasing, right? So let's look at problem A. When you look at this expression, what is the common ratio? 0.75. Is that going to make the terms get bigger or smaller? Smaller. We can sum this. So the sum will be, okay, so we want to start with K is 1. So if we put a 1 in here, the problem says start with K is 1. If we put a 1 in here, what do we get?
3.
Just 3. So our first term is 3, and our ratio is 0.75. So it's 100. I think your sum is 12, if I did my arithmetic right. All right, what about B? What's your ratio? -4/5. We can add it, because even though -4/5 goes positive and negative and positive and negative, each term, magnitude-wise, gets smaller. So it's addable. This sum is going to be the first term, and this time we're starting with n equals 0. So what's the first term? 1 over 1 minus the ratio, which is -4/5. So that's 1 over 9/5. I got 5 9s. Double check my arithmetic. I think that's right. Now what about C?
Can't do it.
Can't do it because pi is 3.14, and 3.14 divided by 2 is bigger than 1. And if your ratio is bigger than 1, you're not summable. These terms are just going to keep getting bigger and bigger and bigger. The only way this formula works is if the ratio has an absolute value less than 1. Otherwise, you can't sum up infinitely many.
So on C, like, how do we answer that? Do we need to put anything? Or we
It says determine whether it converges. It doesn't converge. Yep, can't add it. No sum.
So for the the S equals all that, is that just to be used for these specific equations, or what is that formula for?
This is our formula for infinite geometric series. I had that on the board the other day.
Infinite geometric
Yeah, you should have had that already in your notes since we talked about that. All right. What about this guy? Well, what's the ratio? Can it be added? Yep. So the first term is 1. The ratio is 1/2. So if we added those all up, we would get 2. Now, the last problem we did the other day, I skipped number 4 to go to number 5, to talk about these repeating decimals. There are at least 2 different ways, probably more than that, of changing these into fractions. But one way of changing them into fractions is to think of them as infinite geometric series. So think about breaking this decimal apart into a sum. Would you agree that if I took 1.8 and added 0.07 and then 0.007 and so on, that I would end up with this decimal? Now, the whole thing is not a geometric sequence. This guy is kind of an odd lot, right? He's not part of the sequence, but everything from here on is. Would you agree with me? That that's a geometric sequence. What's the ratio? What am I multiplying by to get from term to term here? 0.1. I'm just adding a decimal place, so that's 1/10, 0.1. So this much of it, right here in the bracket, can be added using the formula I just erased. It's an infinite geometric series. So the sum is the first term over 1 minus the common ratio. Now that's just this bracketed part. So that's 0.07 over 0.9. Now my job is to make a fraction. Fractions aren't supposed to have decimals, so I'm going to move those decimals out of the problem. Would you agree 7/90ths? Now, that is this. Okay? I need to add this still in. So 18/10ths, that's this guy right here, 18/10ths plus 7/90ths. That's how I'm going to get my whole answer. So my formula works on the repeating part, then I have to add in the rest. So let's get a common denominator. So 162/90ths plus 7/90ths, 169/90ths. And that is the fraction, with any luck, if I did it right, 169 divided by 90 gives me that guy right there. So on Friday, or whenever that was that we were together, we did a repeating decimal, but in that problem, the whole thing repeated. So it's easy, we basically did this part. Here, you can only use your formula with the repeating part, and then you have to add the extra part back in. Okay? All right, now we're gonna do some more sums. So I'm gonna write my formulas up here. These are all sums. So I've got this one that I've been using. I got this one. And I got this one. Okay, so first thing I need to do is look at my sequence. This is problem 7A. And I gotta figure out which formula I'm gonna use. So I guess I gotta figure out what kind of sequence I have, or series. What's going on in problem A? It's arithmetic. So this is my arithmetic formula. Note, the other two have R's in them, and what does R stand for? Ratio, so that they're not arithmetic. So that's my arithmetic formula. Okay, so I'm gonna find the sum. There's a critical piece of information missing.
How many terms?
How many terms? I don't know how many terms I have. I know that the first one is 117, and the last one is 33. That's what I need here, first and last. But I have no idea how many I'm adding. Well, remember, you do have another formula. So if worse comes to worse, you can use the other arithmetic formula. Now this isn't the sum. This formula says the last term equals the first term plus the common difference times n minus 1. Will that find n for me?
Yeah.
Yeah. So if you can't figure it out any other way, you can always, 100% fall back on your other formula, arithmetic formula, and it will give you what you need. I got 13, I don't know, is that what you got? So once I know that's 13, then if I think I can add, I can do 13 divided by 2 times. Final answer, 975, does that sound about right to anybody? Righto, I think this is the same problem. I mean, I think we have the same issue, don't we? Now, it is geometric, and it does stop, but I still need to know how many terms I've got. So I know my first one is 3, I know my ratio is 2, I have no idea how many it's gonna take. So, again, one surefire way of figuring out what term it is to rely on your other formula. I said this is one surefire way. This will never let you down. This says that the last term equals the first term times the ratio to the n minus first. What's the first step in solving that equation? Divided by 3, very good. So 4096 equals 2 to the n minus first. What? We could definitely take the logarithm of both sides. And if that works for you, and that's fast and efficient for you, that is absolutely magnificent. Take the logarithm of both sides, 100% that will work. Also, however, peculiar to these kinds of problems, would you agree that n has to be a whole number? Like 8th term, 25th term, something like that. Since we know n has to be a whole number, you can trial and error this if you wish. So 2 to some power has to be 4096. So if it's easier for you to log both sides, do it. Do it. But you can also just say, okay, 2 to the, no, that's too big. 2 to what power would give me 4096? 2 to the 12th? So this number right here, 4096, is 2 to the 12th. This is 2 to the 12th. If 2 to the 12th equals 2 to the n minus 1, then what does n have to be? 13. Now again, in some problems that might be quicker than logarithmic, in other problems that might not be, and it doesn't matter. One way or the other, you have to figure out that n is 13.
So in general for this test, like on homeworks and stuff, does it matter how we solve it?
Nope.
If we show our work and make the right
Show your work. Yep, show your work.
Okay, so you can like write out like each
You
individual.
can, but
it's
if you
like
run out of
between-
time, I'm not happy about, I mean, I'm not gonna fix that for you. You don't get it by time. But yeah, you
But we
could.
can solve this
Absolutely,
without.
you gotta show it. Okay, so 3 minus 3 times 2 to the 13th divided by -1. My sum would have to be 24573, 24,573. So what you got? hopefully. All right, number 6. Well, I don't have any problems in this one, luckily. Is it addable? What's the ratio? 1/2. So yeah, it's addable, and the sum is 12. Okay, what about D? Is D addable? No way! How are we getting from term to term? Multiplying by 3. And what's the rule? If we have an infinite geometric series, can we add it if the ratio is 3? No, no sum for that one. Just because it has fractions in it, kids, doesn't mean its ratio is less than 1. The ratio there is 3. Okay, we got another sigma. And it is also infinite. So I take problems out of different books, and sometimes they put in infinity up here, and sometimes they don't. If it's empty, it's infinity. So store on forever. Can you look at this and tell me what's going on, or should we write out a few terms? A lot of times with sigmas, I like to write out a few terms, like if I put 1 in here, if I put 1 in, I get 3/4. What if I put in 2? 3/16. 3, and so on. Now, some of you can look at that. That looks like a geometric sequence with a ratio of 1/4. And is that what happened? Yeah. So you can tell sometimes by just looking at them, but if you can't, write out the first few terms until you figure out what's going on. Now, is this one addable? It's an infinite series. Is it addable? Yep, because the ratio is 1/4. So my sum will be my first term over 1 minus, ooh, did you get 1 for your sum? I think it is. All right, what about F? See if you can do F on your own. Can you do problem F on your own? Finding the sum, if it's possible, of that right there.
Yeah.
What, I hear a lot of talking, which is fine, totally fine. What are you talking about? Can you add this one? What's your ratio? 2/3? What's your first term? 5? I hope you got 15 as your sum. Easy, easy, easy. Good. Good, good, good. All right, number 8, a little word problem. A ball is dropped from a height of 10 feet. When a ball is dropped, the guy kind of goes like this, but I'm spreading it out on diagonal so I can look at it and it's not all on top of each other. Each time it bounces, so the ball is dropped from 10 feet, it's going to bounce back up. It rebounds 0.95 of the distance it fell. So this right here would be 0.95 times 10. Would you agree with that? And then it falls back down that same distance. Okay, then it goes back up. What's that one gonna be? How high does it go on its second bounce there? 0.95 times 10 times another 0.95, and so on. How far will it travel before coming to rest? So, all this, how far will it travel? If it had a little pedometer on it, how far would it travel before coming to rest?
It starts.
I want you to look at the downs. So the first one was 10, this was 10 times 0.95, this was 10 times 2.95s. So just the blue, which is the downs, is that geometric? Yep, with a first term of 10 and a ratio of 0.95. So just the downs would be 10 over 1 minus 0.95, or 10 over 0.05, which is what? What is that? 200. Now, that is not the answer to the question. What is that? That's all of the downs. Now, what about the ups? Well, could you do the same thing with the ups, except the first up is not 10, right? So you would have to start with this as your first up, but could you do it? Absolutely. What I like to do is, I like to say, well, the ups and downs are exactly the same, except the ups don't have that first 10. So if my downs are 200, then my ups are going to be 190. Does that make sense to you? Now you can certainly work it out again, but I think that makes sense. So what's the total distance traveled by the ball? 390. What if the ball had been thrown instead of dropped? What if it had been thrown? Then the ups and the downs would be the same. All right, we're getting close to being done. A few more things to do here. Number 9 looks interesting. Is it kind of implied that I'm going to be using this formula right here? That is the only formula that adds infinitely many things. Any thoughts? What's the first term?
The radio.
First term would be what? X to the first. What's the second term? And x cubed and so on. What kind of a series is that? Is it geometric? Yep, and what's my ratio? X. We've seen lots like that today. Ratio's X. So, according to my formula, the first term, which is also X, divided by 1 minus the common ratio, has to be 4. First term, you figured out that was X, divided by 1 minus the ratio, you figured out that was X. According to the problem, that has to equal 4. So X equals 4 minus 4X, if I multiply over to there. So 5X equals 4, and it looks like X equals 4/5. Not too bad. learn to write our own sigma for this set of numbers. Okay, we did some of these the other day. The ones we did the other day, I think, were all either arithmetic or geometric. Because what goes here has to be your explicit formula. And if it's arithmetic, you can get it from this. And if it's geometric, you can get it from this. But I don't think that's either one. Now, I'm not saying there's not a pattern there. There's a pattern there. But,
Well, it's, I don't know what it's called, but it's +3, +5, +7, +9,
So that's a pattern. Maybe some others of you saw that. Well, you need to write a formula for it. That's what has to go there. I'd like you to think about something else for a minute. This is the kind of thinking you have to be open to, and it comes with practice. It comes with practice, but you have to be open to kind of looking at those numbers and thinking, okay, what would happen if I added 2 to every one of those numbers? If I added 2 to all those numbers, they would become 1, 4, 9, 16, 25, and 64. Now, what's special about those? They're the squares. So the formula, the explicit formula for the squares is n squared. 1 squared, 2 squared, 3 squared. But I have to then subtract 2 in order to get the numbers that I actually had to start with. I think we looked at one of these the other day. Now, what goes up here? This is not infinite. It doesn't go forever. It has to stop. Can you figure out where it has to stop? 8. Yep. Because if you plug in 8 to your formula, you would get 62. This is the last number. Now, we could have exactly the same idea, but instead of subtracting 2, we might add 1, right? Or multiply by 10 or something, random. So squares, cubes, that's a special group of numbers. Kind of keep that in the back of your mind. All right, we're doing great. We are doing great. We need to do this next problem here, and then a couple from this next page, and then we're going to do that. All right, we're not going to do mathematical induction. We're out of time.
For the
Much
whole
as I would love
unit?
to, please not. All right, so here we go. Number 11.
No, that means we're not.
The table below shows, okay. The balances form a geometric sequence. What is R? Can you find R? Anybody know how to find R? Isn't R the number that you would multiply 20,000 by to get 22,000? So what if we just took 22,000 and divided it by 20,000? And then just to be sure, I'm gonna take 24,2 and divide by 22,000 and make sure it matches, because that ratio has to be the same. And I think it is. The ratio is 1.1, 11 tenths, 1.1, however you want to think about it. Write a formula for the balance in the account n years from the start. The starting point is that 1996 thing. So from that starting point, so the sum of n terms, we're writing a formula for the sum of n terms. You said it's geometric. The first term is 20,000. The ratio is 1.1. Isn't that your formula? It's a geometric series. We know the starting number and we know the ratio. So we'll just plug that in and this will tell me, so if I want to know how much is in there after 10 years, I'll just put in a 10. Oh yeah, that's right. Okay, so then find the sum of the December balances from 1996 to 2006. Now, this I'm not sure about because this is going to be, okay, that's this, I messed up. The term is what I want for that first question. 20,000 times 1.1 million minus first. This is how much money is in the account in 1997, and 1998, and 1999. Yeah.
So that's A.
That's B. That's B. Now C says find the sum. Now I'm not sure why you would want to do that, because isn't my money just staying in the bank and growing?
Yeah.
So you wouldn't find the sum because that would be adding,
The question would
These
make more
together.
sense would be like find the sum of the amount of money.
find how much money is in the account after 10 years.
Yeah.
That would
No,
be,
like find the amount of money that like runs in the account.
oh, how much I've changed, how much the amount has changed.
That would make more sense.
All right, well, I'm gonna do what it says, even though it doesn't make sense to me. It says find the sum, okay, of the December balances. So I need 10 years of that. Oh, inclusive, would that be 11? Yeah. Inclusive means count them both. And again, that does not make sense to me at all, but that's exactly what it says to do, so we'll do it. That doesn't make sense to me, because when I put my money in the bank, I don't add this year's and last year's. This year's is last year's plus some, like Peter said. But anyhow, this is B. This is how much is in the account after n years. And then this is if you just add up all those amounts. For whatever reason. All right, I'm gonna type that in just to make sure we're all getting the right answer. These would be a little tricky to type in. All right, what did you end up with? 370,000, 623, yeah. All right, we have one more thing to talk about, and then we'll be done. So we gotta do problems 12A and B. You are not responsible for memorizing these formulas. But we need to know how to use them, so I'm gonna write them down over here. These are summation formulas that can come in handy when we are adding up things that aren't arithmetic or geometric. All right, so here's what I mean. Let's look at that first problem. And it says that we're adding up 15 terms that are generated by this little explicit formula. So what would the first term be? Remember, this needs to add. So plug in your 1. What is the first number we're adding? 5, okay. Now plug in 2, you might need a calculator here to start helping you there. Plug in 2, and we get 18. Plug in 3. Okay, and that's enough for me to see that this is not arithmetic or geometric. Would you agree with that? Now, I'm going all the way to 15, so whatever this last number is, that would be, when I plugged in 15, it's gonna be something big, that would be it. So what I can do is take this problem, using my summation formulas, I can take this problem and split it apart into 3 pieces. So, add up from 1 to 15, 3n squared, plus from 1 to 15, 4n, plus from 1 to 15, negative 2. So in other words, instead of summing the whole thing, I'm going to sum the individual monomial parts of the polynomial. Furthermore, this is a multiplier, and it can come out in front of the sigma. So 3 times the sum of n squared plus 4 times the sum of n, and then this one's just what it is. So I took this big sigma and I broke it down first of all into each term, and then I pulled the coefficients out in front if there were any, and now this is what I'm left with. Okay, now let's look at this guy right here. Okay, now he's n squared. So right here is my formula for adding up the squares. Okay, so what does my formula say to do? If you are adding up from 1 to n, so for me that's 1 to 15, what am I going to have? What is that sum going to be? This sum right here is going to be 3 times. What am I supposed to do? 15 times 16 times 31 over 6. So that right there is the sum of all of the squared parts of my original problem. Then I will have to multiply that by 3 because I had 3 squared parts. So I'll figure that out in a second. That's one step. Okay, now what about this guy? Now this is just the ends. So what's the formula for adding up just the plain numbers? That'll be 15 times 16 over 2. And then I've got this guy. Now, do not be confused by this guy. What does that tell me to do? Add up negative 2 15 times? Isn't that what it says? Remember my big thing I started with, my polynomial I started with? Didn't every one of those terms have a minus 2 in it? So since there's 15 terms, there's going to be 15 minus 2's altogether. So that's just going to be 15 times negative 2. So now I will figure out each one of these partial sums, add them all together, and that will give me my sum. $4,170. I'm gonna wait on confirmation from somebody. That's Chris Scott. Lucy?
For the, 7 for -2 part, why did you do -2 inside -2? Did you multiply by the term?
No, because this says there's 15 terms in the expression, and every term has a -2. Look back at the original problem. Every term, when you start plugging in your numbers, every term's gonna have a -2. So there's 15 -2s. Just like there were 15 n squareds, but there were actually 45 of those. And so on. Okay, now, you try the last one, letter B. Try that one using these same formulas. Split it up. Remember, you can pull the coefficient out in front if it has one. Use your formulas.
He's in your class. His son is in biology. Which one is he? His son. Oh, goodness, your buddy checked there. Because he's the guy, but he's a concussion or something. For the class. And I'm trying to
Oh, he's right there. He's
Okay, what do you think, guys? Are you coming up with this? So those are pretty cool little formulas. They're gonna let you add up just about anything you want to add up that's written as a polynomial. Because you can split it up. Is it 18? All right, so that's it. That is it. So tomorrow we will start reviewing